Okay, so this is A&I HL using the Oxford textbook, Chapter 9. Chapter 9 is on modeling with matrices, storing and analyzing data. So what exactly is a matrix and what is it good for? Great questions. Well, let's start with what a matrix is. It's not at all going to be obvious at the start what the matrix or matrices are good for until we get relatively far into the subject. In the beginning, it's mostly definitions. So first, what is chapter 9.1? It's on introduction to matrices and matrix operations. Introduction to matrices and matrix operations. We want to know what a matrix is and what we can do with it. The what, I guess what we can do with it is a misnomer because what I'm talking about here is, adding, subtracting, multiplying, things like that. But what we can use them for, that will come later. So first, a matrix. Capital A, we use capital letters for matrices. A matrix, capital A, with dimensions m by n is a rectangular array of real or complex. Now, this is what the Oxford textbook uses as their definition. Numbers, but just be aware as you get more and more advanced using matrices, the entries can actually be anything. They can be matrices themselves. You can have a matrix of matrices. It can get very complicated. But at this level, we're using numbers, real numbers for the most part, sometimes complex numbers, the imaginary numbers. But a matrix A with dimensions m by n is a rectangular array of real or complex numbers containing m rows. So the first of the two dimensions, m by n, the first number, 3 by 4, 3 rows, m rows, and n columns, where lowercase a with subscripts I and j, a sub ij, refers to the elements located in row I and column j. So notice how we use a capital letter for the matrix itself, for the whole object. But if we need to refer to a specific entry of the matrix in the third row and fourth column, for example, A sub 3, 4 would refer to the entry of matrix capital A that appears in the third row, fourth column. And such a matrix is said to have dimension or to have order m by n. Such a matrix had to have order or dimensions. Well, the dimensions are m by n, and we say it has an order m by n. They're synonymous. So a picture would help. A equals, and then we have this shape. It's a rectangle. The first entry is A11. So notice you put a comma in between them. We don't want to think A11. So A11, first row, first column. A12, first row, second column, all the way to A1N, first row, nth column. A12, 2, 1, second row, first column, A, 2, 2, second row, second column, all the way to A, 2, N, second row, nth column, and we go all the way down to A, M1, mth row, first column, all the way down to A, M2, mth row, second column, and then all the way down to A, M, N, mth row, nth column. So this is the first row, this is the second row, this is the mth row, this is column N, column 2, and column 1. Column 1, column 2, all the way through column N. Let's move this down a little bit for clarity's sake, so that I could be a little more LCD-ish. So column 1, column 2, all the way through column N for matrix A. Okay, so here's an example. Of course, there's nothing about the letter A for a matrix, so I can call a matrix by any capital letter I want. So here's matrix P, whose entries are -1, 3, 4, 2, 1, 5, 0, 7, and -3, 4, -2, 6. P is a 3 by 4 matrix, right? So P has order 3 by 4, 3 rows, 4 columns. And in particular, P, that's a lowercase p, P sub 2, 3, the second row, third column entry of matrix P is the number 0. So that's what a matrix is. Another definition. We have lots of definitions here because we're introducing a new type of object. So if M equals N, if the number of rows is equal to the number of columns, we say that the matrix is a square matrix, which seems very, very logical as a definition. We're used to rectangular matrices, but if the number of rows equals the number of columns, then it's a square matrix. So like numbers, we want to know how to add, subtract, multiply, divide if possible, though we're going to see that's a little suspect. Take matrices to power, solve equations with matrices, and then of course, eventually, what's the point? Like, why do all this? But we're going to start by defining what it means for two matrices to be the same matrix. We know when two numbers are equal. Why is 2 equal to 1 plus 1? Because they, at the end of the day, represent the same number. So when are two matrices equal? So matrices A and B are equal if and only if, it's abbreviated in mathematics IFF, if and only if the matrices have the same number of rows and columns or the same dimensions, and not only do they have the same dimensions, but their corresponding elements have to be equal. Your corresponding elements are equal. So the matrices have to have the same number of rows and columns and the same coefficient in every slot. Okay. To add or subtract matrices, they must be of the same order. They must be of the same order. And then you add or subtract corresponding elements. So we are now defining what it means to subtract and add matrices. And very straightforward as an example, if I have the following example, if I have 125, 30, 275, 40, 180, 55, and I want to add that to the matrix 300, 50, 210, 35, 325, 65. The first thing I check is that the matrices have the same orders. They are both, in this case, 3-row, 2-column matrices. So because they are of the same order, we are allowed to subtract in this, or add in this case. And how do we do that? We just add corresponding elements. So 125 plus 300 is 425, 30 plus 50 is 80, 275 plus 210 is 485, 40 plus 35 is 75, 180 plus 325 is 505, and 55 plus 65 is 120. Hey, we just added our first two matrices. Mazel tov. Okay, next. Now, the book says the zero matrix, 0, is the matrix whose entries are all 0. I don't like that. A zero matrix, because there's infinitely many of them, depending on the size. A zero matrix is a matrix, all of whose entries are the number 0. So for example, 0, 0, 0, 0 is the 2 by 2 0 matrix. It's the 2 by 2 0 matrix. Of course, immediately we see our first property that assuming orders are the same, if you take any matrix and you add the 0 matrix in either order, what do you get? While you're thinking about that, I'm just going to go back a couple steps and throw in the symbol for the 0 matrix in the previous definition, a 0 matrix 0. Okay, so now that you've thought about it, a plus 0 equals 0 plus a, you just get the same matrix that you started with back. We also know that a minus 0 is a, and 0 minus a is equal to, well, we should define this, negative a, the negative of the original matrix. But of course, how do we define a negative of original matrix? We define this as the constant -1 times the matrix itself. So we have to define now, a little backwards, we have to define scalar multiplication. So given a matrix, capital A, and a number K, the book says real number, but earlier it allowed complex numbers. So why limit it now? We'll just say add a number K. So given a matrix A and a number K, then Ka, notice that we use a lowercase letter for the number and the capital letter for the matrix, is obtained by multiplying every element of the matrix A by lowercase k, where k is referred to as a scalar. So now that we've defined this new type of object called a matrix, we have to go back and give a name to all of those other numbers that we've been using so far, because now we have a new type of object. So we go back and we call those numbers scalars. So Ka is, well, let's do it this way. This process defines scalar multiplication, because we also would like to define matrix multiplication. So this process defines scalar multiplication. And it's important to understand that when we say scalar multiplication, we don't mean multiplying scalars. We don't need matrices for that. We've been doing that since 3rd grade. We are talking about a scalar times a matrix. So for example, it says 2 times the matrix P minus 5 times the matrix Q equals the matrix 0. The matrix P is the 2 by 2 matrix 1, 2B, 3C, 1. And the matrix Q is equal to lowercase a, -1, -1, and 0.4. And then the question says, find A and B. Well, I'm going to go one step further, and I'm going to say find A, B, and C. I'm going to assume that's another mistake, because there's 3 letters. Let's find them all. Find A, B, C. Find those 3 things. So how are we going to do that? How are we going to find A, B, C? And I just discovered that I can have new colors here that I never knew existed. I'm going to use this one. So find A, B, C. So we have this matrix equation, 2p minus 5q equals 0. We have these 2 matrices, p and q. Well, let's start off by writing it out. 2 times p, which is 1, 2b, 3c, 1, minus 5 times q, which is a, -1, -1, 0.4 equals the 0 matrix. Remember, this is not the number 0. This is the 0 matrix. And it also has to be 2 by 2. Otherwise, the equation makes no sense. So we will, even though they didn't specifically say, hey, by the way, 0 is a 2 by 2 0 matrix, you can't do anything if it's not, so we will assume it is. Now, what comes first? We have a multiplication, we have a subtraction, and then we have a multiplication again. Well, order of operations still holds. We do multiplication before we do subtraction. So we're going to do 2 times the first matrix. Well, how do you multiply a scalar times a matrix? You multiply, as it says here, is obtained by multiplying every element of A by K. We just multiply each element. So 2 times 1 is 2. 2 times 2b, 4b. 2 times 3c is 6c. 2 times 1 is 2. Minus, we do the same thing here. 5a, 5, -1, 5, -1. 5 times 0.4. That's not 0.2, that's just 2. And this equals to still 0, 0, 0, 0. What do I do now? Well, let's subtract these matrices. 2 minus 5a will be the first slot. 4b minus 5 minus -5, so plus 5 will be the second slot. 6c minus -5 will be the third slot. And then 2 minus 2, or just 0, will be the fourth slot. And we want this to be equal to 0, 0, 0, 0. And now, remember the first thing we learned about matrices was, what does it mean for 2 matrices to be equal? It means they have the same dimensions, the same orders, and corresponding elements must be equal. So the only way these 2 matrices can be equal is if 2 minus 5a is equal to 0, 4b plus 5 is equal to 0, 6c plus 5 is equal to 0, and if 0 is equal to 0. Well, obviously the last one works automatically. If it didn't, by the way, we would immediately say there's no solution, because there's nothing you can put in there that will make these 2 things equal. So we're really happy it's equal to 0. The first one tells me that a is equal at 5a divided by 2. So a is equal to, sorry, not divide by 2, divide by 5. A is equal to 2 over 5. The second one, if I subtract 5 and divide by 4, b is equal to -5/4. And if I subtract 5 and divide by 6, c is equal to -5/6. So we have solved for the only a, b, and c's that make these 2 equations equal to each other. Oh, so new colors here. Okay. So with that under our belt, let us now do the exercise. This is exercise 9a. And as always, after giving the question, pause the video, try it yourself, and then check the answer. So question number 1. Question number 1 says as follows. It says capital A, the matrix capital A, is equal to 2, -3, 5, 4, -2, 6. It is a 2 by 3 matrix. Capital B is equal to 3, -4, 5. It is a 3 by 1 matrix. And capital C is equal to 8, 5, 2, -4, 0, 3, 1, -1, 7. It is a 3 by 3 matrix. So if the question was to add or subtract these, I can't do any of that because none of these three have the same order. We don't know how to multiply matrices yet, so we don't even know if we're allowed to. So what is the question? The question says, what is A12? What is A23? What is B31? What is C22? And what is C31? So again, pause. And then let's check. So A12 is first row, second column of A, -3. What is A23? Second row, third column of A, 6. B31, third row, first column, B5. C22, 0. C31, third row, first column, 1. Question 1 is complete. Question number 2. It says the matrix capital Q, and they give us capital Q here. It is a 3 by 4 matrix, 3 rows, 4 columns, 420, 250, 145, 0, 340, 575, 420, 100, 200, 375, 425, 235. So the matrix capital Q describes the number of units of each of 3 products. 3 products. Are those products labeled by the rows or are those products labeled by the columns? Well, it can't be the columns because there's 4 columns. So the first row must be product 1, the second row must be product 2, the third row must be product 3, that are produced by each of 4 manufacturers. Manufacturer 1, manufacturer 2, manufacturer 3, manufacturer 4. Part A, write down the dimensions of Q. Pause it, write it down, check it. Q has order 3 by 4. Rows always comes before columns. B, write down the value of Q sub 24 and describe its meaning. Write down the value of Q sub 24 and describe its meaning. Second row, fourth column, 100. And what is that? Well, it's product 2, manufacturer 4. So it's the number of units produced. Well, let me go back a step. Number of units of product 2 produced by manufacturer 4. And C, find a 4 by 1 matrix capital T. 4 by 1, 4 rows, 1 column. Find a 4 by 1 matrix capital T representing the total number of products produced by each manufacturer. Find a 4 by 1 matrix capital T representing the total number of products produced by each manufacturer. Okay, well, manufacturer 1 makes sum of product 1, sum of product 2, sum of product 3. In total, you add them together, 432, 960. That's the amount produced by manufacturer 1. 5, 8, 1,000, 1,200 it looks like. Hopefully my math is correct for manufacturer 2. 4, 8, 9, 945, 65, 990 for manufacturer number 3. And 335 for manufacturer number 4. That's it for question number 3. I mean, so far, we don't really see any great uses for matrices, but if nothing else, it's a way of listing lots of information kind of compactly. So at least that's something. Let's go to question number 3. Question 3 says, consider the matrices below. There's a bunch of them here. There's capital R, which is 3 rows, 2 columns, 3 by 2. Capital S, which is a 3 by 3 matrix, 3, -2, 1, 4, 1, -7, -9, 6, 2. Capital T, which is a 2 by 2 matrix, -3, -9, 6, 12. U, another 3 by 3 matrix, 8, -3, -2, 6, 7, +2. Let me fix that negative sign. And 0, 1, -1. V, another 2 by 2, which is -2, 0, -4, -8. W, which is a 2 by 3, 1, -2, 3, 3, 2, -1. And X, another 2 by 2, 7, -2, -6, +4. It says, find each of the following if possible. If not possible, explain why. And then it says, check your answers using technology. Technology. I don't know what they mean by that. Put your matrices into a calculator and do it, I guess. So the first one is 3W. This is the number 3, the scalar 3 multiplied by the matrix W. So like before, as always, pause, check, etc. 3 times the matrix W. How do you multiply a scalar by a matrix? Each entry is multiplied. So the order does not change. 1 times 3, -6, 9, 9, 6, -3. B, R minus W. R minus W. So R is 3 by 2, W is 2 by 3. Cannot do it, not possible. They say explain why. Why? Since they have different orders. Even though they both have 6 elements, 3 by 2, 6, 2 by 3, 6, because they don't have corresponding slots, corresponding elements, you can't do it. C, 4 capital U plus capital S. 4 capital U plus capital S. Well, what comes first, multiplication or addition? Multiplication comes first, and I can certainly multiply 4 by U. But before I take my time doing that, I want to make sure that the resultant matrix can be added to S. Now, when you multiply U by 4, you don't change the order, so it remains 3 by 3. S is also 3 by 3, so it can be done. So let's go ahead and do it. I'm not going to rewrite U and S because I have them above. I'm just going to skip a step and do 4 times U, which is 32, plus S, 35. 4 times -3, -12, plus -2, -14. 4 times -2, -8, plus 1, -7. 4 times 6, 24, plus 4, 28. 4 times 7, 28, plus 1, 29. 4 times 2, 8, and -7 is +1. 4 times 0 plus -9 is -9. 4 times 1 is 4 plus 6 is 10. And 4 times -1, -4 plus 2 is -2. And then for D, we have 1/3 T minus 1/2 V. So before I do the math, T is 2 by 2, so 1/3 of that is still 2 by 2 because it's just 1/3 times each element. V is 2 by 2, 1/2 of that is still 2 by 2, so I can do it. And this one, because I anticipate maybe some fractions, no fractions, but still, just not take the chance of making a silly mistake. 1/3 of -3 is -1, 1/3 of -9 is -3, 1/3 of 6 is 2, 1/3 of 12 is 4. 1/2 of -2 is -1, 1/2 of 0 is still 0, 1/2 of -4 is -2, 1/2 of -8 is -4. And now we have a 2 by 2 minus a 2 by 2. -1 minus -1 is 0. -3 minus 0 is -3. 2 minus -2 is 4. And 4 minus -4 is 8. So I get 0, -3, 4, 8. And hopefully you did 2. Question number 4. And the matrix capital P, which is a 4 by 1 matrix with the big numbers 32,450, 18,725, 24,175, and 19,250, describes the prices in dollars of 4 types of cars: car 1, car 2, car 3, car 4. The sales tax rate is 7.5% of the purchase price. This one tells me I might need my calculator, so let's get my calculator ready. The sales tax rate is 7.5% of the purchase price. So A, write down capital T equals lowercase capital p, where capital T represents the amount of tax paid for each car. Well, K is the amount of tax applied to P, and it's 7.5%, which as a decimal is 0.075. So all I need to do here is scalar multiplication. 0.075 times 32,450 is 2433.75. 0.075 times 18,725, which is 1404.375. Well, in dollars, we don't do anything past cents, so we're going to round up to 38. Even though really it's 375, 24,175 times 0.075 is also a rounding up, 1813.13, and 19,250 times 0.075 is 1443.75. Those are all in units of dollars. B, the matrix capital C represents the cost of each car, including tax. Write a matrix equation that describes C in terms of P. A matrix equation that involves C in terms of P. So there's a few ways you can do this. You can either say, ooh, this is just the original purchase price plus the tax, and that's mathematically correct. But that's not in terms of P, that's in terms of P and T. So we're going to replace T with what we know it's equal to, which is KP. And then we're going to factor out the P. Notice there's an invisible number in front of the first P of 1. So 1 plus K times P. So that is the matrix equation that describes C in terms of P. Capital C equals 1 plus K capital P. And if I really wanted to, I don't have to because we have the matrix equation already done. But if I wanted to calculate the cost, I can always plug in P or use the above T and P and get the cost. But they don't ask for it. The matrix equation is complete. It's 1 plus K, where K, of course, is 0.075. So I guess I can go one step further and do 1.075 times P. Question 5. A column vector can be regarded as a 2 by 1 matrix. A column vector can be represented as a 2 by 1 matrix. Let's understand what this means. If you have a coordinate plane, then let's consider the element -3, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. So we have the point P at -3, -6. And what we can do is draw an arrow from the origin to that element. And we call this guy a vector. This is the vector. And normally in vector notation, we would write it as -3, 6. That's the vector notation. 3 to the left, -3, up 6, +6. But we can also consider this as a 2 by 1 matrix, 2 rows, 1 column. -3, 6. So we have two different ways now of thinking of a vector, either as the vector -3, 6 or the column matrix -3, 6. And we're going to label this as capital X for the purposes of this problem. So part A says first, what is 2x? Part B, or II, says what is 1/3 of x? And 3, III, says what is -x? So, as always, you should be pausing and doing these. 2x is just scalar multiplication. 2 times -3x is -612. 1/3 of x is -1, 2. And x is 3, -6. So then it goes to part B. And it says, part B, show each of these points on a graph. Show each of these points on a graph. So let's start with the original point, which was 1, 2, 3, 1, 2, 3, 4, 5, 6. This is the original point. This is the first point, P. So what is 2x? It's 4, 5, 6. 1, 2, 3, 4, 5, 6. It's over here. This is what we got from I. This one here is what we got from II. And 1, 2, 3, 1, 2, 3, 4, 5, 6. This one here is what we get from III. So show each of these points on a graph. And then part C says, make a conjecture about the set of points described by any scalar times x. It's a collection of points that have what property? We want to make a conjecture. So when you look at these 4 points, there's one thing that stands out, assuming that you're a relatively competent artist. There's one thing that stands out about these 4 points in that they all fall along a line. So Kx is the collection, this is my conjecture, the collection of points on the line that passes through the origin and x, or I guess point P. Point P is maybe better. It's the collection of points on the line that passes through the origin and point P. Remember, x is the column vector that represents the point P, but P is the point itself. So it's a collection of points on the line that passes through the origin and P. If you have a point and you make the vector that represents that point, so now you have basically you have an arrow which you can extend to form a line to infinity in both directions. The scalar multiple of that point will be something along that line. That is something that pops up in vector calculus, which you'll hopefully get to one day. And then finally, we have the last question of the section, number 6. It says, find real values of mu and lambda. They say mu times capital A plus lambda times capital B is equal to the 2 by 2 matrix, -8, 12, -10, 4, where capital A is -9, 12, -6, 3, and capital B is 1, -2, 3, and -1. So we are looking for, it says find mu and lambda. What are mu and lambda? Well, mu and lambda, first of all, are numbers. And when we know scalars, when you multiply a scalar times a matrix, you don't change the order. So mu A is 2 by 2, lambda B is 2 by 2. I can then add them. I'm still 2 by 2. And then, of course, it's equal to a 2 by 2. As far as the orders are concerned, this might be possible. I say might be possible because there might be no solution. Just because we have an equation that's valid does not mean that the equation has a solution. So what are we going to do? Well, let's start by writing it. mu times -9, -12, -6, 3 plus lambda times 1, -2, 3, -1 equals -8, 12, -10, 4. So I get -9 mu, -12 mu, -6 mu, 3 mu, plus lambda, -2 lambda, 3 lambda, negative lambda, equals -8, 12, -10, 4. And this gives me -9 mu plus lambda, -12 mu minus 2 lambda, -6 mu plus 3 lambda, 3 mu minus lambda equals -8, 12, -10, 4. And because these two matrices are equal, corresponding slots must be equal, and I have 4 equations. -9 mu plus lambda equals -8. -12 mu minus 2 lambda equals 12. -6 mu plus 3 lambda equals -10. And 3 mu minus lambda is equal to 4. So now I don't even care about the original matrices anymore because I have reduced the problem to 4 good old-fashioned basic algebra equations with 2 unknowns, which means we have essentially 2 possibilities here. I mean, in theory, there's 3 possibilities. There could be infinitely many solutions if all 4 of these lines are really the same line in disguise, much like x plus y equals 1 and 2x plus 2y equals 2 are really the same line in disguise. What if all 4 of these are the same line in disguise? Then we have basically a line and there's infinitely many solutions. Or 2 of these are redundant, but the other 2 give us 2 lines that intersect at a single point. Or there's no redundancies, there's a contradiction, and there's no solution. So let's start by taking any 2 of these equations and solving them. And I'm going to take the first and the last. The reason I take the first and the last is because those are already prime for a elimination, because the coefficients in front of the lambdas are already equal, or in this case, negatives of each other. If they were equal, I would subtract them to get them away from each other, to cancel each other, I mean. Right? They're equal, 5 and 5, for example. 5 minus 5, 0. But because they're negatives of each other, I can't subtract them, but I can add them, and that will make them 0. So let's add these 2 equations. -9 mu plus 3 mu is -6. Ooh, I wrote that wrong. That should be at mu. -6 mu plus lambda, and negative lambda is 0, and -8 plus 4 is -4. Divide both sides by -6, and I get mu is equal to 2/3. So if there's a solution, then mu has to be 2/3. Let's plug it into the last equation. 3 times 2/3 minus lambda equals 4. 2 minus lambda equals 4. Lambda equals -2. So if there is a solution, mu must be 2/3 and lambda equals -2. Let's check it. The first one. -9 times 2/3 plus -2. -9 times 2/3 is -6. -6 plus -2 is -8. Ooh, we got a good situation there. -12 times 2/3 minus 2 times -2. -12 times 2/3 is -8. -8 minus -8 plus 4 is negative. Did I make a mistake somewhere? Well, that's embarrassing. Let's go back, check my work. -12 mu minus lambda minus 2 lambda. Did I write something wrong? -8. Oh, let me pause it for a second for me to find my silly mistake. And hopefully you caught this long before I did. But you'll notice that it was -9, +12 back in A. And I've been writing -12, -12, -12. in a lot of places. -12. So I just corrected all those to make them +12. Okay, so 12 times 2/3 is 8. 8 plus 4 is in fact 12. Okay, now it works. -6 times 2/3 plus 3 times lambda is -2. -6 times 2/3 is -4. -4 and -6 is in fact -10. So that works too. And 3 times 2/3 minus -2. 3 times 2/3 is 1. Sorry, 3 times 2/3 is 2. 2 plus 2 is 4. And sure enough, we have solutions. So all four of them work. And we have that mu is equal to 2/3 and lambda is equal to -2. So hopefully this has illustrated the basic ideas and also shown that it's very easy with so many numbers flying around to make a mistake when you copy things over. So be careful about that. And if you get something that doesn't work, it does not automatically mean that you did it wrong. I mean, it doesn't mean that your strategy was wrong, but the first thing you should do when numbers are not working out properly is go back and check your work and make sure that you did it correctly. So this takes care of 9.1, and I will see you soon for 9.2.